Okay. So shall we start?
Yeah.
Okay. So very good morning, one and all. At the outset, I would like to welcome all of you to this today's lecture on SWEBOK, stands for Software Engineering Body of Knowledge, Evolution and Machine Learning, Software Engineering, including Design Patterns and Goal-Oriented Analysis. The today's speaker is Dr. Hironori Washizaki. It is my pleasure to invite him to this today's lecture. Let me give you a brief introduction about Professor Hironori. Dr. Hironori Washizaki is a professor and the Associate Dean of the Research Promotion Division at Waseda University in Tokyo. And he is a visiting professor at the National Institute of Informatics. He is also works in industry as outside directors of System Information and Xmotion. Hironori currently serves as IEEE Computer Society First Vice President 2023. He was awarded Golden Core Member and Distinguished Contributor from IEEE CS. He is a leading professional and educational activities, including development of the Guide to the Software Engineering Body of Knowledge, which shortly called as SWEBOK, educational courses and certification programs. He has published more than 200 research papers in refereed international journals and conferences, including in IEEE Computer, IEEE IoT Journal, TETC, EMSE, SICO, ICSE, and ASC. He has led many industry, academia, joint research, and large funded projects in software design, reuse, traceability, and quality assurance. He is a leading professional IoT AI educational project called Smart SE. Since 2015, he has been the convener of ISO, IEC, JTC1, SC7, WG20 to standardize bodies of knowledge and certifications. He is currently running for IEEE Computer Society President-elect 2024. The election will close on 11th September 2023. This is the brief introduction to Professor Hironori, and it so happened that we could interact with each other about the paper that he has recently published on envisioning software engineering training needs in the digital era through the SWEBOK version 4 Prism. In fact, this article is a very comprehensive article providing various insights about the various knowledge areas that the software engineering curriculum should have. And in fact, the article also contains the various teaching methods to incorporate these knowledge areas. So thank you, Professor Washizaki, for taking your time, accepting our invitation in spite of your busy schedule. I know that you are tightly occupied with your the presidential election to the IEEE CS, and I wish that you would be the IEEE CS president in the next year. Thank you very much for accepting, and floor is yours.
All right, so thank you, Professor Aswani. Thank you for Chairman. Thank you for having me, and this is my great pleasure to join and also having this opportunity. So today, I'm very happy to talk about machine learning software engineering and also machine learning design patterns, and also somewhat, if time allows, I may also just briefly introduce about some goal-oriented analysis, machine learning-based systems. And so I'm Hironori Washizaki, and I'm basically working at Waseda University, and as Professor Aswani mentioned that, yes, currently I'm running for IEEE Computer Society President-elect 2020 election. So let's begin. So yes, I'm currently working at Waseda University, but at the same time, I also work in the industry as outside directors of System Information and also Xmotion. Those are software companies. So actually, I know both academia and also industry. That is very important, especially software engineering shall address not only academia side but also industry side, and so that's why I'm working at both sides. And also I'm doing some professional contributions, particularly in IEEE. I'm currently IEEE CS First Vice President to lead activities and future directions, and also and particularly I'm currently leading the evolution of Guide to the Software Engineering Body of Knowledge, or in short, SWEBOK Guide. So later I will introduce what is SWEBOK Guide and why SWEBOK Guide is important, and how we are going to evolve SWEBOK Guide. All right, so can I have just few minutes about my position statements about election, because it is truly important for me. And so if I elected as IEEE President-elect 2024, then I'd like to promote CS membership to get more engagement. Yeah, especially, we are in region 10, right? Region 10 is Asia and in India, and also I'm also in Japan, and it is very important to have various, different, and members, and not only senior members, also regular members, and even junior members. And so I'd like to establish strategic directions, and also launching ambassador program. That is my currently, I'm currently planning that. And this picture shows how CS ambassadors can recruit, for example, K-12 students, and then those students can be involved as computer society juniors. Okay, and then finally CS computer society juniors would step up to the computer society members, such as student members. And so it is very important to have more and more attention, especially targeting young generations and early career professionals. And also we need to expand academia and industry, government, society collaborations across over societies and external entities, including ISO. So that's why currently I'm working not only in IEEE, but also ISO and so on. So that I'm very good at connecting different societies such as ISO, IEEE, IPSJ, that are society, IT society in Japan, and so on and so on. Oh, and also we need to enhance activities that define and promote value of knowledge and related professional activities. Okay, so I'm at a very good position because I'm reading evolution of SWEBOK guide, software engineering body of knowledge. So I believe that it is very important that IEEE Computer Society continues to lead that way. Okay, and last but not least, we need to strengthen digital open science and environment. Okay, so open science, that's a very key trend, right? Almost every country, every region, every society is moving towards that direction, such as open everything, okay, such as open source, open reviews, open standards, and open access. And so that kind of, and of course this is the era of digital. So I call that digital open science. So I believe that IEEE Computer Society can lead the way of establishing some kind of research bus, okay, and then to have easy access to executable knowledge base based on digital open science. All right, so these are my position statements. So if you are IEEE Computer Society members, please consider both, and also please spread the word. Okay. All right. So then as I said, I'm currently reading the evolution of SWEBOK guide. So firstly, I'd like to mention, introduce, what is SWEBOK guide and how we are going to evolve SWEBOK guide. Okay. Then in the evolution, particularly machine learning and AI is a very important topic. Of course, everyone is talking about AI and ChatGPT and so on. So and particularly, I'm going to introduce a couple of topics such as machine learning software engineering, including machine learning design patterns, and if time allows, then multiple goal-oriented machine learning system modeling. Okay, so first of all, okay, what is the guide to the software engineering body knowledge, or in short, SWEBOK? Okay, so it was originally established in early 2021 or 24. And so the objective includes guiding learners, researchers, and practitioners to identify and have common understanding on generally accepted knowledge in software engineering. And also, SWEBOK guide defines boundary of software engineering. In other words, what is software engineering? What is not software engineering? That is very important. And also, SWEBOK guide shall be a kind of foundation for further certification and also educational curriculum, right? For example, here, this is a university kind of seminar. So such educational curriculum shall be aligned with very solid foundation. So we believe that SWEBOK guide can be a very good foundation for such certifications as well as educational curriculum. So this picture shows at the beginning, we have a lot of, islands of knowledge, right? Okay, for example, here's a testing technique, here's a programming technique, here's a coding technique, something like that. But in reality, islands of knowledge are not so, meaningful, right? So we have to combine them and do something meaningful in the actual, software development. So we have to combine them into activities and practices, and finally, then practitioners can do some tasks and activities. So body of knowledge is here, right? So okay, so which knowledge exists and how we can combine them. So we have to guide practitioners and even researchers to think about the broad area of software engineering. And actually, SWEBOK guide has been already adopted in many ways. For example, at the PCS software professional certification programs based on SWEBOK. There are such as associate software developer, professional software developer, and also professional software engineering master. And also, SWEBOK guide has been adopted in many ISO standards, such as ISO IEC 24773 Part 4. All right, so then this picture shows how body of knowledge is related to some other related concepts. So usually body of knowledge is composed by multiple knowledge areas, such as software testing, software requirements, and so on. Then each knowledge area is composed by multiple topics, such as unit testing, integration testing, and so on and so on. And last but not least, then each topic usually refers to some reference materials, such as books, articles, magazines, and so on and so on. Okay. Then usually body of knowledge can be seen as kind of a system connected to skills, competencies, and jobs and roles. So, for example, IEEE Computer Society is currently providing running courses based on body of knowledge, but also software engineering professional certifications. So once again, SWEBOK guide can be a foundation, foundation to organize such different concepts such as knowledge, skills, and competencies. So then, what is the evolution? Okay, so because latest SWEBOK guide has been published 2014, almost 10 years ago, actually 9 years ago, 2014. And in the last decade, we see a lot of evolution of software engineering, software development, such as Agile is becoming kind of de facto, and also DevOps and security is becoming more and more important, and also ChatGPT, AI is incoming, and so we need to reflect such modern software engineering and also practice change, update, and also BOK, body of knowledge is still growing, and so. Here's a list of knowledge areas in SWEBOK version 3. Then we are going to evolve it to reflect such recent change in last decade. For example, we are going to add at least 3 knowledge areas: software architecture, software operations, and software security. Software architecture, yes. Well, actually, software architecture is a very classic topic, but it's time to emphasize its importance more and more. Okay, because now software systems are becoming more and more complex and very complicated and very dynamic, such as IoT software systems or machine-based software systems. There is the one topic today, and so by considering such nature with complexity of those very complicated software systems, we have to clearly address software architecture. So that's why we decided to emphasize such importance of software architecture by adding software architecture knowledge area. And also operations. Yes, this is an area of DevOps, and almost any software is firstly released and then evolved, and even during the runtime, and so we have to emphasize such importance of software operations. And last but not least, software security. Yes, well, actually, software security was originally a part of software quality, of course. However, of course, this is the era of internet of everything, or internet of things, and So almost any software has been connected via internet. Okay, so it means that any software system is facing more and more security challenges, so security vulnerabilities, attacks, and so on and so on. So that's why we decided to emphasize the importance of software security by adding software security knowledge area. And then, okay, then what about Agile and DevOps? Okay, so we decided not to have independent knowledge area. Rather than that, we decided to have it as a kind of cross-cutting concern, okay, cross-cutting, a crossover different multiple, almost any knowledge area. For example, okay, what about testing? Yes, there's an agile testing, okay? Okay, so what about security? Okay, there's a practice about agile security. So like this, agile is not just one technique. Well, our agile is not just one practice, but agile is a kind of mindset, okay? And it is actually related to almost any life cycle stages, any phases, and any knowledge areas. Therefore, we decided to have it as cross-cutting concern rather than independent knowledge area. And last but not least, okay, so what about AI? Well, actually, we discussed a lot about that. And we decided that it is too soon, okay, too early to have independent knowledge area dedicated to AI software engineering. However, of course, we have to say something, okay? Therefore, we decided to add some topic into computing foundations knowledge area rather than having independent knowledge area dedicated to AI and software engineering. All right, so this is the very brief overview of evolution of SWEBOK guide. So if you are interested about SWEBOK guide, then please join us. So soon, at the latest, middle of September next month, we are going to have end-to-end public review of this SWEBOK guide. So it is time to have your voice, okay? So your opinion or your input. Hey, for example, you are missing this topic, or it's better to have additional explanation, or we want to hear your voice. Okay. Of course, there's no guarantee that we can address any comment, but we love to hear your voice. Okay. So later we will have a public review. All right, so for example, here's an example of new knowledge areas. For example, software security. Okay, this knowledge area is composed by multiple knowledge areas, topic areas, actually, such as software security fundamentals, software security management organization, software security engineering processes, security engineering and software systems, software security tools, and domain-specific software security. All right, so you can see that firstly, yes, indeed, very basic security knowledges are all covered by this knowledge area, right? From fundamentals to management, organization, process, and system tools. In addition, it is truly important to mention about very domain-specific security, because security measures and security techniques are quite depending on each different specific platform and domain, such as, okay, what about cloud? What about IoT? And what about machine learning-based applications? Security measures and security techniques could be somehow different. Therefore, we decided to have this topic area, domain-specific software security. So we believe that this new knowledge area can be a very good basis for structuring further certification, education program, training program, and also industry processes, and also organizational standards. All right, then okay, then what about AI and software engineering? Okay, that is a main topic of today. So, well, actually there are two different but related directions. One is AI for software engineering and software engineering for AI. Okay, so actually, like that, software engineering and AI are mutually related to each other. Okay, so AI for SE is about to establish effective ways of building high-quality software systems by replicating human developer behavior. Okay, so actually that's a quite traditional usual software engineering endeavors supported by AI. For example, what about cost prediction, or when we can release this software or risk assessment supported by AI, or that's a quite usual AI adoption in software engineering. And then an emerging area is SE for AI, software engineering for AI. So there's a need for particular support of software engineering for AI, such as interdisciplinary collaborative teams of data scientists and software engineering, software evolution focusing on large and changing data sets, and ethics and equity requirements engineering. So especially particularly, I'm going to focus on the second one, software engineering for AI, because that is a very promising but very challenging, emerging topic. Okay, so this is so we finished first topic, and I think we well actually I'm happy to take a question anytime, but I may continue my talk, right?
Yes,
Okay.
yes. You can continue. Yes.
Okay, good. Okay. So all right. So then as I mentioned that there are two directions: AI for software engineering and software engineering for AI. Okay. Then now we are going to focus on software engineering for AI, especially machine learning software engineering. It is about software engineering for machine learning based systems or machine learning based applications. So yes, indeed, it's time to think about machine learning software engineering. We need something. Why? Because there's a dramatic paradigm shift. Okay. So, well, we can say that from the viewpoint of logical thinking, conventional software engineering is a kind of deduction based. Okay. So, yeah, we can say that, okay, here's the initial goals or some requirements. Okay, then based on that, okay, we can design some software design models or something, or even program. Okay, then based on that, software systems behavior will be defined, right, based on that model. Okay, then the software systems behavior will produce some data. Okay, and then such data will be used for defining the predefined model. So again, it's a kind of very deduction-based approach. All right, then what about machine learning software engineering? So it can be seen as induction or even abduction-based approach. So, well, it is quite same that at the beginning we need to have some goals, right, or requirements. After that, at the beginning, we cannot define any model because we don't know what is the correct model. Instead, we can have some data, huge amount of data. So it's a kind of data first rather than model first. Then, based on data, by applying some machine learning algorithms, we can have some model. Then, based on that model, software systems can define their behavior in somewhat probabilistic way. So you see the clear difference between the conventional software engineering and machine learning software engineering. Machine learning software engineering. Is it deduction based or induction based? So in machine learning software engineering, so you see that data first rather than model first. So its probabilistic behaviors derive emerging quality or validation concerns. So quality aspects can include, of course, data quality, and those are truly active research topics because model and behavior are truly depending on data. So data quality is truly important. And also machine learning system development challenges so well discussed in these years by conducting empirical case studies. But still we need more practices and patterns for particularly industrial, professional software engineering. So that is the second topic today. So okay, so this picture shows a very abstract, view of machine learning-based system. So firstly, let's say that here's the infrastructure software system, and based on that, by having training data, huge amount of training data, okay, then we can have some trained model, by inference and applying the machine learning algorithm. such as, of course, deep learning, but not only deep learning, but also a very classic, machine learning algorithm as well, such as SVM, decision tree, and so on. All right, then, and based on such trend model, okay, then once we receive some new data, okay, then trend model will infer, right, and make some prediction or some analysis. Then, okay, so here, so are bunch of quality challenges, well, related to each part of in this field. So, for example, in terms of entire infrastructure software system, right? We have to validate architecture, and also we need to ensure quality from the viewpoint of architecture. And actually, it is not so quite different from conventional software engineering. But such architecture analysis and architecture design, architecture evaluation shall take considers nature and aspect of machine learning and also data. And also in terms of data, yes, as I said, behavior of machine learning based systems truly depend on data, training data, and also new data, right? So we have to ensure the quality of data. So then there are a lot of quality challenges such as testing oracle problem. Yes, indeed, it's very hard to say, okay, what is the correct behavior about this new input, new or this new data, right? If it is easy to say that, then machine learning is not so necessary, right? We can have very deterministic rule-based systems. That's it. But since we may have a lot of different variety of different inputs, so that's why we wish to employ some machine learning model, right? So that's why we encounter testing oracle problem, and also we have to ensure some balanced data set and also coverage. Okay, and also in terms of trend model and prediction inference, yeah, then we need to consider performance, robustness, explainability. Yes, explainability is very important. Because often, very accurate machine learning models are not so interpretable, right? For example, what about deep learning models such as CNN or RNN? It's sometimes very hard to say why this is anomaly and why it is not, or it's hard to interpret. Okay, so and also in terms of prediction and inference, we have to ensure that how the final prediction or inference result would be actually aligned with original higher goal. Okay, sometimes there is a gap between project or requirements and actual machine learning based inference or prediction. So we have to ensure some alignment. So then in my talk I will introduce a couple of techniques to address these quality challenges, such as machine learning model repair or debugging technique, and also modeling technique as well. And last but not least, yes, patterns and practices. Those will address almost any aspect of such quality challenge, such as architecture, model, data, and so on. All right. So then, firstly, when we talk about quality challenges, we have to clearly define what is quality, right? And of course, in traditional software engineering, you might know that there is a well-defined quality standard, that is ISO IEC 25010. Okay, sometimes it is called as square model. Okay, that clearly defines what are major software quality attributes, such as functional suitability, performance efficiency, compatibility, usability, reliability, security, maintainability, and portability. Okay, those are well-defined quality measures for almost any software system. All right, so then, of course, machine learning-based applications, machine learning-based systems are software too, of course. Therefore, those conventional quality attributes can be also applied. However, this is important. In addition to traditional nature of software quality attributes, but also we have to address very new emerging quality attributes dedicated or specific to machine learning. So that is addressed by very new ISO standard. That is ISO IEC 25059, and it is just published this year. And it is about AI system quality, product quality. Okay, so if you are handling any machine learning-based system, then you better to refer to this standard because this standard clearly defines major quality attributes necessary for any AI-based system and software. So then there are some key highlights. So for example, in terms of functional suitability, functional correctness, and also functional adaptability have been added or extended. Why? Because, for example, what about correctness? Okay, so it is very important that because machine learning model cannot predict always 100% correct, right? So we have to incorporate some sort of error or some inaccurate prediction or output. So we have to embrace such error, right? So that's why some sort of functional correctness must be addressed. And also in terms of usability, you can see the user controllability and transparency. Those have been newly added to this model, AI system product quality model. Why? Because yes, controllability by users is very important for any AI system, okay? And also transparency, yes, it is also the key. And it will also somehow related to some ethical things and so. And also robustness in reliability and also intervenability and security. So as you see that, once again, we can adopt existing software quality attributes. However, at the same time, we have to consider additional attributes or additional aspects of AI software system quality, such as functional correctness, adaptability, controllability, transparency, and so on. All right, so then what about quality in use? Okay, so quality in use is about the quality attributes from the viewpoint of end users rather than developers. So end users will consider effectiveness, efficiency, and of course, yes, they have to satisfy, right? Satisfaction, freedom from risk, such as some ethical risk and also safety risk, and last but not least, context coverage. Because yes, recently any software system can be deployed and used in various multiple different contexts or environments. All right, so then again, there are some addition to the quality in use, such as transparency. Okay, once again, transparency is the key, okay? And also in terms of freedom from risk, yes, societal and also ethical risk mitigation that has been added to this AI system quality in use model, such as accountability, fairness, transparency, professional responsibility, promotion of human values, privacy, and so on. So by referring to those standards, especially this standard ISO 25059, then you can clearly define necessary quality attributes of your machine learning-based system or even AI-based systems. In addition, as I said, data is the key, right? Because especially machine learning-based system, any behavior is depending on the quality of data. So it is very important to measure data quality in addition to measure the quality of software and systems. So you might know that in terms of data quality, there is a well-accepted standards, ISO 25012, okay? That defines various data quality attributes, such as accuracy, completeness, consistency, credibility, currentness, accessibility, compliance, and so on, okay? So, okay, once again, those quality attributes can be applied to, of course, almost any machine learning and also AI-based software systems. However, in addition to that, we have to consider more. So there are currently additional data characteristics and even dataset characteristics currently under consideration to be added to ISO standard. For example, in terms of additional data characteristics, such as relevance, data scalability, context coverage, timeliness, identifiability, and auditability. Those are currently under consideration to be added to the ISO standard. In addition, dataset is very important, right? Such as training dataset, testing dataset, and for example, how those datasets actually represents actual nature and the coverage of the possible inputs. And so there are multiple quality attributes considered for or dedicated to dataset characteristics, such as balance, yes, balance, or how biased, or that is very important challenge, and also effectiveness of a dataset, similarity, and as I said, representativeness. So then, okay, then back to this picture. So basically, in this very abstract structure, I mentioned that here's an infrastructure software system, and based on that, they are trained model by using training dataset, and also prediction or inference by using new data, right? Okay, then ISO 5259 part 2 is going to define data quality measures and data quality attributes dedicated to AI system. And also, in terms of infrastructure software system and also model and prediction, ISO 25059 AI system quality, product quality, and also AI system quality in use can be applied. So I'd recommend you to take a look at these standards to consider what is the necessary quality attribute, and also how you ensure such quality in your future AI and particularly machine learning based software system development. Okay, so then and actually in my previous research, I conducted a very preliminary study on practitioners' insights on such quality attributes. In other words, how actual industrial professionals are concerning such quality attributes or not during the machine learning based software systems. So we surveyed 300 or more developers, and we got 46 answered in machine learning development. And okay, so these charts shows that how many practitioners particularly concerned some particular quality attribute. And the top quality attributes include functional suitability, maintainability, security, reliability, and usability. Okay, so those are quite reasonable. And so okay, so what about the machine learning model quality, such as robustness, explainability, and accuracy? Those are also well considered by practitioner industry practitioners. So, all right. So as you see that practitioners are now going to consider those quality attributes such as robustness in terms of machine learning model, and also maintainability and also functional suitability and correctness. Okay. So then the next question is, okay, how we test them and how we ensure them, and if there's a problem, then how to fix them. Okay. So well, today's time is somehow limited, but I'm going to introduce multiple very promising techniques. One is metamorphic testing, and another is machine learning model, especially deep learning model repair. Okay, So metamorphic testing is a testing method based on metamorphic relations. Metamorphic relations are kind of relationships whereby changes to the input can predict changes to the output. So okay, formula can be like this. So if we identify that, okay, here's a transformation targeting some inputs such as X, okay, then we may expect some similar transformation targeting output. If we can expect such relationship between change of input and change of output, okay, that is so-called metamorphic relation, and then we can test a lot of different scenes and scenarios and situations. Okay, so here's a here's a typical example. It was presented many years ago, IEEE 2018. So yes, 5 years ago. So okay, so this is about testing machine learning-based automotive software. Okay, so left-hand side, okay, so this is the original image given to the machine learning model. Okay, so yes, indeed, the road is quite straight. All right, so of course, the software automate self-driving software should not change any direction, right? Just go straight. Okay, then but what if there is some rain or some noise? So based on metamorphic relation, we may artificially add some noise, such a kind of rain from left to right. Then by adding such noise based on rain, that self-driving software based on machine learning model made a mistake, okay, to change direction from straight to left, turn left. So okay, so actually by such additional testing, we see that here we can say that we can identify some bug or defect in machine learning model in some very particular case. So actually there are a lot of possible metamorphic relations. For example, that example was about adding noise. Even we add some noise, but we expect no change in output. Okay, that is another. This is a very typical metamorphic relation. Or what if if we input similar inputs, okay, then we expect very similar outputs, right? All right, so these are all metamorphic relations based on past experiments or practices or knowledge, and because machine learning-based systems encounter testing an oracle problem, so it is very hard to specify correct output for each particular input. It is almost impossible, right? Therefore, we have to rely on such metamorphic relation. For example, if we add some noise, but still the output should be same, for example. Or if we change input slightly, okay, then the output should be slightly changed. That is another metamorphic relation. So like this, since when we test machine learning-based systems, it's very hard to specify correct exact output for each input. Therefore, instead of having testing oracle, and instead of specifying expected output for every input, we better rely on such metamorphic relations. And indeed, metamorphic testing is applied to many machine learning-based systems. So and it is very accepted in especially machine learning software engineering community. All right, so then once we identify some bugs or defects in machine learning systems, then especially machine learning model, what we have to do? What we do? So that is about new, especially when we talk about deep learning model, we have to fix or we have to repair neural networks or neural network based model. Okay, that is so-called neural network model fixing or repair. Then, okay, of course, the most easiest and very classic approach is retraining and online training or online run, right? Well, that is a very straightforward method, but often very time consuming and very costly. And also there might be some possible side effects, right? So, once you retrain the model and then suddenly the output could be different, even for the same input. So that could be a inevitable side effect of retraining or online training or online learning. So then, okay, then what about data augmentation, such as data generation or particular data set selection or expansion? And well, also those are also very well studied and very promising techniques. And it's a kind of a try and error, right? And without direct modification of model parameters. But those approaches might be somehow potentially vulnerable to adversarial examples. And then, last but not least, in emerging promising approach is direct modification of machine learning model, especially deep learning model parameters according to specific samples. Okay, so please take a look at these figures. Okay, so okay, let's assume that we are currently building a kind of deep learning model. Okay, of course, based on neural network. Then firstly, we calculate average of neurons output values for successful case only or successful data. Okay, for example, all right, this is cat and this is dog, and all right, so cat and dog have been very classified. Okay, so those are very successful cases. Okay, then only in those cases we can calculate average of parameters and output values. And in contrast, we can also do the same thing for only the failure case. So right-hand side shows average of neurons output values for misrecognition or misprediction case. So then by comparing those two averages, successful case and failure case, then by calculating delta difference. All right, so this figure shows the difference. Then, okay, so particularly we can identify some particular neurons having significant difference between the case of successful and the case of very failure. Then, and for example, in this case, particularly there are particular neurons could have high priority for further fixing. So once we identify those particular neurons, then having different parameter values or output values for the case of successful and also failure case, and then we may just directly change the output or parameters. So that's a very quite straightforward approach to fix or repair neural network and also deep learning models. All right, so this is a very simple idea, and actually there's a lot of state of the art, based on this very simple idea. And if we are interested, then you may refer to okay, actually these are not so new, but exist latest papers and approaches. And all right, so here's a summary of the second part. So so yes, machine learning needs software engineering because we are currently see a paradigm shift. Okay, so I recommend that to refer to quality model to clarify quality requirements and evaluation measures such as ISO 25059 air system product quality and also quality in use, and also ISO 5259 part 2 That is about data quality measures dedicated to AI system. Okay, so then once you clearly define requirements, quality requirements for AI system, particularly machine learning-based system, then of course you need to consider then quality techniques, right? Such as I mentioned, metamorphic testing, and also DNN or neural network fixing or repair techniques. And also last but not least, I mentioned that indeed practitioners are currently considering some particular quality attributes such as maintainability, correctness, robustness, and so on. So, but since this area is just emerging, so we have to establish more and more practices and also well-accepted patterns that can handle such multiple quality attributes. That leads into the third part of my talk. That is machine learning design patterns. Okay, so then time is limited, and I simply go to the next part. So actually, I'm the pattern guy, so I can talk about pattern almost all day, but okay, so time is limited. So the concept pattern was originally invented in not software, but actually architecting and also building and in such area. Okay, so please take a look at these two pictures. Left-hand side was taken from if I remember correctly, some Paris or somewhere. Okay, actually I forgot that. And right-hand side was also taken from another city, maybe not Paris, and maybe somewhere, maybe US. Okay, then so you see that there are some commonality, but there are some differences, right? Then by doing abstraction, yes, because we are all computer scientists, so we love abstraction, right? Computer and software engineering, based on abstraction. So when we do abstraction for these two cases, then we can identify what is common problem and what is a corresponding common solution. So for example, here we can see that okay, so these two cafes are different, okay, of course, and also locations are different. Implementations are different, but we can see that similar problem and similar solution because they need to have a place where people can sit lazily, under the sun and also watching the world go by, and that's a kind of street cafe, right? So the corresponding solution is encourage local cafes to come together and make them intimate places with several rooms and open to a busy path or busy street. So that's the concept of street cafe. So the concept street cafe can be very common, but its implementation could be different in various different cities and environments or even locations or places. So this document encapsulates such common problem and corresponding solution. So this is so-called a pattern. Okay, so this pattern is actually named as street cafe pattern. So that concept was originally introduced by Christopher Alexander. He's a professor in the architecture and also building. But actually, those patterns can be also combined to constitute a language, like English or Japanese or every language consists of various vocabularies, right? So okay, so what about when we discuss about architecting or even city planning or city design, we may have a conversation like this. Okay, so attracting many people to our city, small public squares should be located in the center, and at such small public square, okay, let's make street cafes be open to the street. And so yeah, you see, this is a very quite possibly conversation, right? But I highlighted some key terms such as small public squares, street cafes, and opening to the street. So indeed, those are actually all well-documented patterns. Small public square, yes, there is a pattern. Street cafe, yes, it is a pattern because it encapsulates recurring, very frequent problems, very common problems, and corresponding solutions, and opening to the street. So like this, actually patterns are not islands. So by considering such combination of those patterns, then we can constitute a language to have a much more fluent conversation. Like, okay, let's make small public squares and street cafes and blah, blah, blah. So that's a conversation based on patterns. So I believe that since machine learning-based systems are very complicated, and also it needs various participation of different disciplines such as data scientists, software engineers, hardware engineers, and domain experts, and so on. So we need common language. So I believe that patterns can be such common language. For example, okay, so let's take an example of designing machine learning system, particular machine learning system. So let's consider that we assume to identify the type of instrument, musical instrument for the sound picked up by the cell phone, and achieve recording and response according to the type. However, of course, our cell phone was the memory and performance of the cell phone is limited, and so a large deep learning model is unlikely to be loaded. So what we can do? So possible solution is that, okay, we can communicate. Okay, so let's use two-stage predictions, where a small model on the cell phone determines if a sound is a musical instrument, and a large model on the cloud classifies the type of sound only if it is a musical instrument. And then for the large model on the cloud, we can adopt transfer learning, okay, to achieve very precise, accurate classification. So finally, based on such conversation, we can have this design here. This is a very entire system design, including machine learning model. So here's an audio clip. Okay, then firstly, cell phone or very embedded device can determine is it an instrument or not instrument. And only the case of instrument, okay, then at the cloud, we can classify the sound much more precisely. So that is so-called two-stage predictions. And indeed, this is truly popular pattern, right? Almost everywhere, this two-stage prediction has been adopted. For example, what about, you may say, okay, Google, right? Okay, Google, can you reserve the dinner tomorrow night? Or so then, firstly, your smart speaker or your smart device will firstly determine whether or not the given sound, given voice, it was wake word or not, okay Google or not. And if the given sound was wake word, okay, then at the cloud, there is a transfer learning based model to precisely classify and analyze the instruction, such as reservation of dinner. So or what about IoT-based systems, right? Well, in IoT systems, a lot of data can be almost in real time. IoT devices and sensors can sense data, right? But it's very hard to transfer every data to cloud, because it is really costly, and so it is too much. Therefore, usually, firstly, at the IoT or edge side, do some very simple prediction, right? So the given situation is anomaly or not, okay? At the cloud, at the IoT device side. And if it is likely anomaly or some unusual case, okay, then IoT device or edge device will transfer, the data to the cloud. Okay, then at the cloud, there is a very huge, large, transfer learning based, classification model to analyze more precisely. Okay, what is this anomaly, and what is the cause of the situation, and what we can do, what we can, repair or fix the problem. And so that is another case of, adoption of two-stage predictions with transfer learning. So like this, these patterns, were almost well accepted, and we can use those practices as patterns in a very basic conversation. So, as I said, machine learning software engineering needs more such patterns. There are two reasons. One is that, as I said, actually already, it shall bridge between abstract paradigm and very concrete cases. Right. Indeed, in machine learning software engineering, there are a lot of very, well, not so a lot, but there are some, very abstract, policies. At the same time, there are a lot of very concrete, case studies, tools, and code examples, and or even, Stack Overflow-based discussions. And okay, so well, one is very abstract, and another is very concrete. So we have to do something to fill the gap between those two quite, different things. So I believe that patterns are well good documents to fill such gap by documenting know why, know what, and know how. And also, so patterns are really good tools to reuse solutions, recurrent solutions, and problems. And also, it leads to getting consistent architecture. Because by having patterns, you don't have to consider different solutions every time. Okay, you can have a very consistent solution for the similar problem. Another reason is, as I mentioned, common language patterns can be for any stakeholder, such as software engineers, data scientists, domain experts, network engineers. They are usually using different languages. But as a project, we have to have a very common language. So I believe that software patterns will play a very important role of common language. So while indeed in these last years, researchers and practitioners started to study best practices, striving to design machine learning system and software. So, and actually there are not so a lot, but there are some machine learning system architecture and design patterns defined at different abstraction levels. But those are not so well classified and studied. Therefore, my team conducted a survey of software developers and a systematic literature review to identify what are major machine learning architecture and design patterns, and how those are well accepted or not in industry. So finally, we identified around 15 software engineering patterns for machine learning applications. We call them SEP for MLA. It stands for Software Engineering Patterns for Machine Learning Applications. So the summary was published at the IEEE Computer last year. So if you are interested, then you may refer to our paper. And so we classify them into 3 categories: topology patterns. Topology patterns are more like architecture patterns. So it defines entire architecture, while model operation patterns are more about operating in how to addressing data and models, while programming patterns are much more about very detailed design of such as training infrastructure, serving infrastructure, and so on. So by conducting systematic literature review, targeting academic and also grade literature, we identify around 40 documents, and we identified 15 software engineering patterns for machine learning applications. All right, so then this matrix shows how each pattern is addressing different quality attributes. Okay, yeah. For example, okay, so time is limited, so I may not discuss details, but Yeah, for example, in topology patterns, there are multiple patterns, such as different workloads in different computing environments. Well, indeed, that patterns is well accepted. For example, Facebook or recently Meta is adopting this pattern and also distinguish business logic from machine learning models. There is another architecture pattern, okay, or topology pattern. But each pattern could address different but multiple quality attributes. For example, the first pattern would address performance and also maintainability, while second pattern address maintainability only. And you can see that by our analysis, most of patterns address performance, reliability, and maintainability. In other words, there are some quality attributes to be addressed more, should be addressed more in the future, right? So we need more patterns to address some specific minor quality attributes, such as security and portability, and so on. All right, so for example, I may introduce some few examples. For example, okay, what about architecture topology? Okay, we identify one good pattern that is distinguish business logic from machine learning models. Yes, perhaps you can consider the nature of this pattern. So it is very important to isolate business logic specific parts from machine learning specific part. So this structure, this architecture clearly separates what should be clearly separated from machine learning specific parts, such as user interface, business logic, and also database, while some other parts could be machine learning specific, such as data collection part, data processing part, inference engine, of course, and also data lake. So this architecture clarifies a very basic structure to address business logic based on machine learning model. Okay, and by adopting this architecture, then you can separate the business logic and inference engine and achieve loosely coupling. Okay, therefore it leads to high maintainability and also extensibility of the entire machine learning system. All right, so then what about the problem pattern? Problem pattern is more about detailed design. And here's a typical example that is encapsulate machine learning models within rule-based safeguard. Okay, so once again, you can imagine what is the meaning of this, right? Because as I said, machine learning system software engineering is quite different from conventional software engineering because machine learning software depends on data, okay? And so its behavior is truly probabilistic, okay? Therefore, if we wish to adopt machine learning model into very safety critical systems, such as self-driving system or traffic light control system, and then we cannot simply rely on machine learning model, of course. Therefore, we need some safeguard. So this architecture shows such combination of machine learning model together with deterministic rule-based safeguard. So right-hand side shows encapsulate machine learning model, and that produce some inference or prediction. However, such prediction result is not directly used for final outcome. Instead, there is a safeguard based on deterministic rules. And indeed, this is a quite well accepted pattern. For example, Apollo's self-driving object detection system, and so this is a very typical combination of machine learning-based model and a very traditional deterministic rule-based model. All right, then last but not least, what about model operation pattern? So okay, here's also another typical example about a model operation pattern that is explainable proxy model, or formerly known as deployable canary model. So as I said, explainability is becoming very important, right? And especially when we talk about deep learning model, it is truly a black box, and it's hard to interpret, especially for stakeholders. It's hard to see, why this is good and why this is not good, and it's hard to interpret the result. So in addition to production model, we sometimes need to employ canary model. In other words, explainable proxy model as a proxy to approximate the output of the production model. Okay, so canary model has less accuracy but much more explainability, and then always input all in same stream into those two models always, and then always we can check the difference by monitoring and comparison. And if there is a significant deviation, if there's a significant gap between those two outputs, okay, then we have to do something, such as retrain canary model as well as production model. So that is a explainability technique, and well accepted for example, in Japan, there is a application of this pattern in the image-based anomaly detection system at a factory. So like this, okay, so patterns are not an invention. Rather than that, patterns can be identified in existing software systems. And not only our achievements, but also there are some other endeavors to identify more and more patterns. For example, Google engineers identified as a much more primitive machine learning design patterns, such as model training patterns, problem representation patterns, resilience patterns, reproducibility patterns, and responsible AI patterns. So if you're interested about such primitive patterns, then you may refer to this well-known book titled Machine Learning Design Patterns. And actually, it is a really good book. Therefore, I translated this book into Japanese to promote those patterns, even in Japan. All right, so here's a summary of this part. So, as I said, machine learning needs patterns. That I believe. Okay, so that's why I identify machine learning patterns addressing specific quality attributes that are not handled well. For example, especially security, usability, and explainability, those are not so well addressed. So we have to do something more, such as identifying and constructing more patterns, and also yes, we have to consider what is the actual impact of those patterns on the quality attributes. And also we need to analyze more and more relationships among patterns, because as I said, patterns are not islands. So we have to identify relationships or dependencies among those patterns more and more. But last but not least, we have to integrate those into a framework. Okay, so that leads to our final the final part of my talk. So as you see that, okay, so in machine learning software engineering, there are quality attributes we have to consider, and there are some quality techniques such as metamorphic testing, and also model repair, DNL repair, or DNL fixing, and also there are patterns and practice coming more and more. Okay, so then the last question is, okay, then how to integrate those different things, different concepts, techniques, patterns into one system? Okay, that's a question. So yes, indeed, in machine learning system development, we have to consider business concerns, of course, but also system concerns, software concerns, and traditional software concerns, and machine learning software concerns, such as I said, such as quality attributes and architecture pattern, and so on and so on. So the question is how to align those different decisions, in consistent way, and also we have to trace, back and forth. So we are currently working on a project about machine learning system modeling framework. So okay, so this slide shows our latest framework to address 6 dimensions: values, augmentation, safety, goals, architecture, and machine learning, ML ops. ML ops is machine learning and operations. So, such as in terms of value, we address our AI project canvas, and also safety case for augmentation, and also stamp STPA for safety, and also goal models and architecture diagram and machine learning canvas. And so yes, for the single machine learning system development, we have to address such multiple different views, such as not only performance or robustness, but also safety, and also goals and project goals, project requirements, and in consistent way. So And also such, modeling, such as requirements modeling and also architecture modeling shall be aligned with actual modeling, training, and evaluation results. Okay. Therefore, at the same time, we are also working on integration between modeling and machine learning pipeline. So the concept is that firstly, okay, so engineers do some requirements and analysis design. Okay, then yes, indeed, we already established the machine learning training pipeline by using DBC. Okay, so DBC is a very well accepted data version control, but also workflow management, open source tool. Okay, so then based on that, we can easily do some training and do evaluation. Okay, then at the beginning, okay, so maybe the accuracy is not so good. Okay. Okay, for example, in this case, okay, we misclassified some, images, particular images. All right, then what we have to do? Conventional machine learning, development is that just try and error, quite ad hoc, right? Okay. So for these images, okay, what we can do? So maybe change parameter or adding more training data, and that's quite ad hoc. Instead of such very ad hoc process, in our framework, we firstly visualize issues. So what's the problem and where's the problem? Then adding some strategy based on quality techniques, such as repair or metamorphic testing. And then, for example, in this case, do repair. All right, then we can confirm some improvement. For example, okay, this image is now, correctly classified. And such results can be again well visualized. So that is much more, systematic way to, model requirements and architecture together with actual machine learning performance. So that is, what practitioners need. We believe that. So we are currently doing some case study and also actual industrial, adoption. So if time allows, I may introduce, but okay, so time is somehow limited. So okay, so this video shows kind of a very short demonstration of our tool currently we are building. For example, here, currently engineers doing some modeling, higher goals and also project requirements, and then at the same time in background, we can do some pipeline. Okay. Okay, so time is limited, so let me skip. Yeah, okay. Then machine learning training, model training, and also evaluation results will be visualized on the architecture and requirements model, like this. Okay, you see that. Okay, here we see a lot of issues on not only architecture but also project requirements, and so it means that some requirements and also architecture part were not well satisfied. All right. Okay. Then doing some strategy such as repair in this case, then we can confirm. All right. So far, oops, very quick, but okay. So finally, you see that still we have some minor issues highlighted by red. However, you see a very smaller number of issues have been visualized, right? So like this, our framework can achieve a very systematic and well visualized procedure and process of machine learning based system development. Okay, so it's time to conclude my talk. So in my talk, I firstly introduced the evolution of SWEBOK guide, and as a part of that, I also introduced machine learning software engineering and also software engineering for AI. Okay, because we see some significant paradigm shift. Okay, and then as a part of machine learning software engineering, I introduced some particular quality techniques such as metamorphic testing and also neural network model debugging or repair, and also machine learning design patterns. And by the way, don't forget your vote if you are IEEE Computer Society members, and its president election will end on September 11th. Okay, so thank you. Thank you for your attention, and I'm happy to take any question. Thank you.
So thank you very much, Dr. Hironori, for the wonderful talk, providing various insights into how software engineering is working towards AI-based systems, and also about AI for software engineering. So the two dimensions, you have given in the very beginning, and subsequently you have focused on software engineering for AI. And I'm sure that our participants have got enough insights on that. And any questions, please raise your hands, and then you can ask the questions. Participants, please. Any questions, please? Either you can type in the chat window or please raise your hands. Okay, in the meantime, I have a couple of questions, Dr. Hironori. Number one, the current industry is moving towards, we get inputs from the industry talking about low code and no code paradigm. So when it comes to this aspect of low code and no code, is it that we have to view this as AI for software engineering dimension of it?
Okay, so Professor Swani, that's a truly important question, and indeed a suggestion was indeed, not only about AI and machine learning development, but no code and also low code platforms are quite incoming and becoming very popular. Of course, in Japan, and also I guess also in India, and also quite worldwide movement. And same is true for machine learning software and system development. For example, for example, having just few parameters specification. Okay, then engineers don't have to code by using Python, or so that low code or no code based machine learning model development. So yes. And that leads to much more wide adoption of machine learning and also software engineering in industry. And however, still we have to take care of especially its limitation, because low code no code means that we can't do everything, right?
Yes.
But by limiting some so actually low code no code is a kind of model transformation. So we have to firstly limit the scope, and we have to accumulate the transformation rules. Okay, then we can do something only if the target context fits well within the target scope. So well, in other words, if we wish to handle additional some smart things or additional extended things, then we cannot simply rely on no code and low code. So perhaps it's time to think about some kind of combination of such very basic low code no code part, but also some very advanced smart technologies. So maybe in the near future, perhaps software engineering will focus much more about some possible integration, right? No code, low code with traditional professional development.
Yes. So I have one more question about while mentioning about the ISO IEC 250-59, you mentioned about the standards. I wish to know, are there any metrics and measures? Say, take an example. You mentioned about context coverage. So are there any metrics to measure that, whether the system is met this particular measure or not?
Professor Swan, that's truly a good question, and the answer is yes and no. So yes means that yes means that for some of quality attributes, yes, practitioners and especially as standardizing committee is defining some popular metrics, how to measure some context coverage, and also, example, in this case, function adaptability. So for some attributes, yes, but for other particular quality attributes, well, it's not so easy to identify, define common measurement. And so the answer is yes and no. So for some of very popular quality attributes, easy to measure, okay, then we can easily identify popular common measurements. While for some other very specific quality attributes, for example, what about transparency? how to measure that,
How
right?
to measure, yes.
Someone would argue that, oh, it is not transparent, but someone could argue that, oh, this is very transparent. So maybe for such, especially new additional quality attributes, maybe it's too early to identify, common measurements. But well, yeah, let's do something together and to identify some common.
Yes. Yeah, and I have one more question. You mentioned about the rule-based system. I have a point. Generally, the AI and ML community has come forward from rule-based systems to more automated these things. I'm just wondering, the rule-based model here.
Okay, that's also a very interesting question. Right. Well, actually, in machine learning model, it's quite broad. Okay, so actually, machine learning model can include a very traditional, rule-based model. Can be also seen as machine learning model. Okay. So right. Actually, okay. So the boundary between, so for example, in this case, rule-based safeguard. So the boundary between encapsulated machine learning model and rule-based safeguard could be sometimes somewhat unclear. That's a very interesting discussion. And also sometimes without very explicit safeguard, but machine learning model itself tries to have some kind of rule base or a kind of safeguard inside, not outside, but inside the machine learning model. That is another research direction currently happening in the machine learning community. And so perhaps this pattern could be applied in various different in very quite a different implementations with different machine learning models.
Right. So dear participants, in fact, I have enabled for you guys to interact with Professor. So you can unmute yourself and you can ask any question that you have.
Professor, sorry, but I gotta go because I have another meeting.
Yes. Fine.
Yeah.
Okay. So in such case,
but I'm happy to take any question.
Any question, one question, maybe
via email or
yes. If any question you have, you can always interact with Professor Hironori. And thank you very much, Dr. Hironori, for a wonderful talk. And as Professor Hironori mentioned, those who are members of IEEE, in fact, please do vote Professor Hironori, and we can get valuable contributions from him. Thank you very much, Professor Hironori.
Thank you so much. Thank you for having me. This is my great pleasure.